Hello, in this video we're going to go over two really important mechanics concepts being forces, force stuff, and conservation laws. These are two really important concepts and like techniques to know for solving problems in mechanics and all kinds of stuff outside of what's directly mechanics. You can do so much with forces, with conservation of momentum, conservation of energy. And so understanding how to use those is really one of the big concepts to focus on. You really want to feel good about these before the IB exams. Um, all right, if you're looking for other mechanics stuff, I do have another video that's like all the data booklet equations in mechanics. So I'll break down all the equations there. But for this one, we're going to talk about these two concepts and how to think through them and apply them. Okay, so we'll do forces first. And the main like kind of rules about forces that you want to know are Newton's laws. They do love to have you know Newton's laws, do memorize them, be able to state them and kind of understand what they mean. So the first law basically says if your acceleration is zero, if your net force is zero, then you move at constant speed in a straight line. That's called translational equilibrium. So object in motion tends to stay at motion, object at rest tends to stay at rest, that whole thing, unless there's a net force. Okay, this is really just, again, net force equals zero. Then you'll have no acceleration, so you'll either stay at rest or stay moving in a straight line at constant speed, not changing your direction or speed. Okay, Newton's second law is make sure you know that this is how you say it. It's officially this. It's officially rate of change of momentum. Maybe it's also worth knowing how that turns into F equals ma when m doesn't change, but that's really Newton's second law. Net force is equal to the rate of change of momentum. So yes, this turns into F equals ma in most cases, but that's what it is, so just make sure you can say that. Okay, and the third law is kind of the harder one, but the rule is easy. For every action, there's an equal and opposite reaction, but you really have to think about what this means. You have to, if they say anything about a Newton's third law pair, an action-reaction pair, which of these forces has to be the same by Newton's third law, you have to do this method. The force of object A on B equals negative force of B on object A. Yeah, so they're the same size, but in opposite directions. You're going to screw these up. Your brain will screw these up. Otherwise, you're going to be thinking about multiple forces on one object. All right, and this is another general rule about forces and a way you want to think about forces. To define a force, you must have two objects. A force is one thing pushing or pulling on another thing. If you can't, always like pause and think about this. If you can't name the two objects that are pushing, what's pushing and pulling on what, then you don't really understand what you're talking about with the force. So make sure you can really think that through. When I talk about the force of gravity, the force of friction, the normal force, what is pushing on what? You should always be able to name and understand A and B to understand how to do forces. That's harder than it sounds. So try to practice and think about that as you think about forces. Here's a great example one. See if you can do it or if your brain betrays you. Okay, there's a tire swing hanging from a tree by a rope. The rope holds it up. There's a tension force of 20 pounds. What force must be equal and opposite by Newton's third law? So think about it, pause the video, see if you can name the force. Okay, if you said gravity, that's super wrong. That's exactly what they want you to pick, but that's wrong because it has nothing to do with gravity. You're thinking about multiple forces on the tire. Okay, you got to do A on B thing. So here's what you do. The force of tension is the force of the rope on the tire. This is the rope pulling physically up on the tire. The only rule that Newton's third law says is that the tire is pulling down on the rope as much as the rope was pulling up on the tire. That's always true. You go sit in that tire now, right? And the rope will have to pull upwards more. The tire will pull down more on the rope, but the weight of the tire doesn't change. Okay. If I cut the rope, the weight of the tire is certainly not equal to the tension in the rope. Yeah, but these two forces are always the same. They'll change together if there's any changing happening. Yeah, so those two forces are always the same. The trick with these sometimes, if you're ever talking about gravity, right, assuming we're on the Earth, the weight of the tire would be the force of the Earth on the tire. That's what gravity is. It's two masses pulling on each other, right? And so the Earth pulls down on the tire with a force of 20 pounds. The tire pulls up on the Earth with the weight, force, we should say, of 20 pounds. Yeah, and yeah, pounds are a unit of force. Obviously, when we're doing math, we usually use newtons, but pounds is force. So think about force that way. Okay, those two forces are also equal and opposite always. That's how you do Newton's third law. Try not to screw them up. They're tricky. Do the A and B thing. You always have to think about them like that. Okay, when you're doing F equals MA, you've heard me rant and rave about this before. F equals MA. F doesn't just mean force. F means net force, the sum of all the forces, and you got to do in one dimension at a time. So you either sum all the X forces, and that tells you about the acceleration in X, or you sum all the Y forces, that tells you about the acceleration in Y. You have to make an FBD for these, and if there's anything at an angle, you got to break it into components so you can turn everything into equivalent X and Y's. Okay. Always make an FBD. If you're just plugging in any old F into F equals MA, you're likely to do it wrong. Here's another one. I think this is a repeat from that other equation video. So try this real quick, see what you get. Okay. The way they want you to do it is like this. They want you, well, the trick, I guess, the distraction is this. If you just think F equals MA means F equals MA, you'd be like, hey, look, I have an F and an M. So I would just put 60 newtons and 8 for M, and I would get A as 7.5. That's absolutely wrong. That is not what F means, right? I got to draw an FBD, and I got to think about my little mass falling through the air. There's going to be a drag force on it, yes, but the other force I got to know is there, that's always there, is the force due to gravity, aka the weight of the object. I definitely want to know that I just use m times g to calculate weight near the surface of Earth. This is a paper one, so I'm just going to use 10 for g. So this is about 80 newtons pulling down. The net force then is 20. The net force is 20 down. That's what acceleration depends on, the sum of the forces, not just any one force. Yeah, so I have to sum the forces, solve for acceleration. I get negative 2.5 because it's down. That just means direction. There, we could possibly define down as positive 2, so definitely B is the answer I want to go for here. All right, so net force, net force, net force. Other fun force stuff you're going to do, they love the incline plane. It's a good one. This is usually the way you want to break it up. We do this tilted coordinate system thing because, so most forces want to, and especially the acceleration, the main thing is if this thing slides down the ramp, it's going to accelerate this way. I don't really want my acceleration to be at an angle. It gets messy. So we tilt our coordinates so that X, usually we call it, you can call it whatever you want, but let's call it X is parallel to the plane and Y is perpendicular to the plane. Then I'll sum all the forces up and down the ramp, and I'll sum all the forces into and out of the ramp. Okay, because if this thing rolls down and I get something like friction, it's probably going to go, if it's sliding down, the friction is going to go this way, right? So that would be like along this line. If I got a rope and I'm pulling it up the ramp, then I might apply a force this way. If I'm pulling it up a ramp, then the friction would even be this way. Yeah, so don't like memorize the like these different forces, you know, which way friction is, which way the applied force is. It depends on what's happening, right? The thing you do want to be comfortable with, though, is the trick to these is always taking your weight vector, which is going to be the only thing at an angle now, since weight is always down, straight down towards the center of the Earth. And I break that into the piece of the weight perpendicular to the ramp and the piece of the weight parallel to the ramp. When you do this, this is your right angle. Okay, practice doing that. Make sure you're comfortable with that. A lot of times I see students try to make the right angle here. That's definitely not what's happening, right? Think about what you're doing and why you're doing it. We're making a component parallel to the ramp and a component perpendicular to the ramp. So those are the two angles that are at 90 degrees. So this 90 degrees would go here. Okay, this is equal to the ramp angle. That just kind of memorized. There's a fun geometry thing that happens there. But, you know, think about if the ramp angle was 0 degrees, it should make sense that this would also be 0 degrees. If that helps, but just kind of remember that. All right, and you want to do your SOHCAHTOA now. The Y component is, let's see, on the adjacent side of this right triangle compared to the hypotenuse, right? So I would do some cosigning with Y. Remember, weight is equal to mg. So this stuff, you know, this is going to be mg cosine of the angle. And same reason this is opposite side. If I make my right triangle, this will be mg sine theta. You do want to be pretty quick about SOHCAHTOA stuff like that at this point. If you got to write out sine equals opposite over hypotenuse and go from there, you can, but try to practice this enough that this becomes almost second nature. Okay. Um, oh yeah, don't do this. The normal force doesn't equal mg. There is no formula for the normal force. Okay, this happens a lot, and so it's easy to get in the habit of just doing this. But in this case, it's definitely not, right? Look at my forces. There's only two forces in y, and I'm not moving in y in like this, perpendicular to the ramp direction, or else the box would be coming off the ramp or going into the ramp. Yeah, so like officially, I would do my net force in y, right, equals may. This is 0. My acceleration in y is 0, so the normal force is as big as that y component of gravity, right? This happens a lot on the ramp because usually you don't have something like crazy like this. Okay, but again, don't memorize like a formula for the normal force or even lots of formulas for the normal force because there isn't one. You have to make an FBD to find the size of the normal force and compare it to everything else because it's a reaction. That's what R stands for. It reacts to all the other forces happening. Okay, so there's some net force idea stuff. One more force that comes up that you do want to be familiar with is the drag force. Key thing to know about drag is that it's proportional to speed, and it kind of depends on the type of drag. The IB doesn't usually get into this. It depends either on V or V squared, depending on the type of drag. But really, you just want to know faster means more drag, which is pretty intuitive. If you picture, sticking your hand out the window when you're driving, slow versus fast, right? Faster, more drag. What that means is as you speed up, the drag force increases, which gives you that fun idea of terminal speed. It's opposite your velocity. It's not necessarily opposite anything else. It's opposite your velocity. So if you're moving in a weird, if you have a projectile moving in an arc or something, the drag force is constantly changing its direction. It's a resistive force. That means it's opposite your velocity, not your displacement or anything else. They're usually the same, but not always, right? They like to do this double negative thing, so just read those problems carefully. It's hard to tell sometimes. They'll say the air resistance is negligible or air resistance is not negligible, and that would mean you have to account for it, right? So that's a little annoying, but just watch out for, pause and make sure it makes sense whether or not you have to worry about drag. All right, and these are good to conceptualize these graphs. Make sure you can think about what happens when there's drag, when you're like this would kind of be in free fall with drag, we should say, pretty specifically, but that's a specific example that comes up. So anyway, you hit terminal speed because as you go faster and faster, the drag force gets bigger and bigger and approaches the size of the weight, right? And once the drag force and the weight are basically equal to each other, your net force is close to 0, so you're not accelerating anymore, which means you're going to hit terminal speed. Okay, and it's all very limity and calculusy when you really get down to it. So it's all asymptote stuff, but for the most part, you want to be okay with, if I drop something and there's drag, it's going to start from rest and it's going to go faster and faster and faster. Everything's negative here because we're just saying, I suppose down is negative. You could for sure see these graphs all flipped on across the x-axis, right? So with positive y values, it would mean the same thing. But you're going faster and faster and faster and faster, but at a slower and slower rate until you hit terminal speed, right? Should make sense then that, our acceleration would start at g and approach 0 over time. The displacement's the kind of tricky one, but think about your tangent lines for this one. The thing I always think about is terminal speed. So I know it starts at rest, so it's got to start off flat, and it ends at some constant speed, so it's going to end with like a more or less constant slope, but that slope is like the gradient, we should say, is getting steeper as time goes on until you hit a constant speed. Okay, so try to be able to apply those ideas on your motion graphs and in problems. They're not going to make you math really with drag unless they just give you a number for the size of the drag force. It's usually more, they say, a qualitative approach, though. So you talk about how a resistive force will affect whatever's happening in the problem. Okay, and then to conservation stuff. So F equals ma are really, really good for when you have, an unchanging sort of situation on one object. So you're looking at one object, and you can talk about the forces that are acting on it and how that causes an acceleration. And then you can all do all kinds of fun stuff. Like if you find acceleration, you could maybe SUVAT, or even vice versa. You can SUVAT to find acceleration and then do some net force stuff. So it's really good for going between those things. But if you have something more complicated, like a collision, or where there's a force that's changing, or when you have a system with multiple objects and you're not just looking at one thing that's being pushed and pulled and what happens to that one thing, right? You have two things crashing together, or a thing that you drop and it bounces on the ground and then comes back up. You can't FBD that really unless you're just looking at the instant it's on the ground. Yeah, because the forces are changing. Okay, so if you have something like more complicated, a system, changing acceleration, stuff like that, conservation laws are really good for those, because all the craziness that happens, like when the ball hits the ground or when the cars smash together or whatever, you don't have to worry about, because conservation laws just say you take a beginning point, you take an end point, and like say the total energy maybe should be the same, or the total momentum should maybe be the same. You can really do some simple stuff with a before and after. Yeah. So if you got a changing situation with a before and after, often trying one of these conservation laws is a good thing. The more you practice them, you'll just get used to when to use what, but that's a kind of rule of thumb. Okay. Conservation of energy. We're going to do the initial and the final energy thing. Just remember, you have to think about the objects in your system, and energy is a physical thing. It's not just, they don't always just trade off. You don't want to get in the habit of thinking this thing doesn't have potential energy, so it must have kinetic, or vice versa. That's not a thing. Okay, all it is this: if it's moving, if there's something moving, it has kinetic energy. If there's something some distance off the ground, right, it has gravitational potential energy. You should probably also add, if there's like a spring that's compressed or stretched, it has elastic potential energy, right? And that's it. Okay, those are the rules, and so you just add it up. If you don't have any work being done on your system, so there's no external force coming in and adding energy, and there's nothing like friction doing negative work to take energy away, then initial should equal final energy, but you can account for any energy gained or lost by, adding this term over here, the little W for work. All right, so that's for work. Yeah, so that's conservation of energy, and it's for everything in the system. So if you have like two, ping pong balls that are bouncing off of each other, or, bouncing on the ground or whatever, you add all of their potential and kinetic energies together at the beginning, add all of their potential and kinetic energies together at the end, account for anything that added or took away energy from your system, and you got yourself a little conservation, and you can figure out whatever you need to figure out. Okay, momentum, similar. The key word to look for with momentum is collision. So if you see collision, it's a conservation of momentum situation almost always. Maybe some impulse stuff. Usually those go hand in hand, because impulse is change in momentum, right? Okay, in a collision, momentum is conserved, and really, momentum is always conserved in a collision. Is a good rule of thumb, and then in general, in a system, momentum is conserved so long as no net external force acts on your system. Yeah, and that's kind of another way of saying Newton's second law, because remember, net force equals rate of change in momentum. Okay, look out for these words: elastic and inelastic. In an elastic collision, kinetic energy is conserved as well as momentum. Momentum is conserved in both of these, but in an elastic, kinetic is conserved. In an inelastic collision, kinetic energy is not. So you can do initial kinetic equals final kinetic for elastic collisions, and you might have to, but in inelastic, that's not true. In the collision, you lose some energy due to heat or sound or whatever. If the two objects stick together, that's a hint that you definitely are looking at an inelastic collision, because there's energy tied up in the crumpling of the things and them sticking together due to friction or something like that. Okay, and like we were saying, you just want to think about all the objects in your system when you do conservation. You're not looking at just one thing like you are when you're looking at an FBD. Right, this is maybe the tricky thing for conservation laws. You're looking at all objects. For F equals ma, it's one object only. Right, you're looking at all of the forces on one object and how they affect the acceleration of that one object. So, I mean, you could do multiple FBDs and multiple F equal MAs if you have multiple objects, but usually more than one thing, you're looking at conservation rules. Okay, usually none of those are hard and fast rules. But okay, let's do one example of a good little conservation one that's pretty common. This is from a paper 2. All right, and so I have train cars crashing together. Okay, so there's like an earlier part, but it doesn't. You don't need any of the numbers or context for this. It's just there's an engine pushing trucks like um, locomotive cars. Okay, so the engine gives truck X a sharp push. X moves along a horizontal track and collides with the stationary truck Y. And they're going to stick together. That's what tells me right away inelastic collision. As soon as I see one thing smashes into another and they stick together, I know that this is an inelastic collision. I'm going to do conservation of momentum. That's the thing to do when they give you this setup. And they move off with the speed v, so they move together with that speed. So I have the following data: the mass of each truck, the speed just before the collision. Okay, I want to calculate v, which they defined up here, so make sure I read that carefully. That's the speed of the two trucks moving together. Okay, always make a sketch with these. Sketching this will help a lot, even if you think it's like a simple, straightforward one. It doesn't hurt to real quick make a little sloppy sketch and be like, okay, I start with X going this way at, what was it, 4 meters per second. And this guy is 3.7 thousand, so 3,700 kilograms. It's going this way, and I got truck Y, call it U. Initial speed is 0, 6,300 kilograms at rest. Okay, and then later, so you always make a before and after. So this is before and after. Okay, the actual details of like the force happening during this collision and all that kind of crazy stuff is nuts. There's like a changing force. I get one of these like impulse graph situations where the force is kind of like nothing, and then it's a lot, and then it's nothing. And I couldn't really F equals MA this correctly to do anything with it. It's too complicated, but I don't have to worry about that. I just look at the before and after. What happens at the end? All kinds of crazy collisions happen, but then I just get one big, stuck together truck of X and Y together, moving off with some speed V. And that's going to have a total mass of, this is nice, 10,000 kilograms. Okay, so now I can think about my conservation of momentum, because I know that's what I'm going to use to calculate V, because that's always what happens when I have this setup. And think about what I have and what I need. So I'm going to do initial momentum equals final momentum. So my initial momentum is of the whole system. So my whole situation, I look at and say, what's all the momentum going on here? This would be more exciting if car Y was also moving, because then I would do, mv for X and mv for Y and add them together, remembering that momentum is a vector. So like if, let's say this thing was moving 1 meter per second to the left, it would have a negative momentum. This would have a positive momentum. Yeah, so just don't remember that stuff is vectors. I should probably do this. Okay, so what it's going to be is the initial momentum is just 3,700 times 4. This guy is the only one that's got momentum. I'm using mv for momentum. And that equals, the final momentum is, again, I'm going to do m times v. Now the mass I'm talking about is this combined mass of X and Y. So I got 10,000 times v, the v that I'm searching for. All right, so the math is easy now, but setting all that up is me understanding what's going on. So I'm going to do this, divide by 10,000. And also just think about this, makes sense to me that I'm going to end up, a little less than half of my initial speed of 4, because I more than doubled the mass that's moving. That went from 3,700 kilograms moving to 10,000. So it's almost triple, right? I should be down by more than double, less than 3 times. And yes, if I calculate this out, I get 1.48. I'm going to round that to 2 sig figs and say I get 1.5 meters per second is my speed. Okay, and then here, determine the kinetic energy lost as a result of the collision. Same deal, if I'm talking about lost, I have to think about initial and final, right? A change. And so really I'm talking about a change in kinetic energy. I know I lose kinetic energy because this is an inelastic collision. That's kind of what they're getting at. And so I'm going to do final, whoops, not momentum though. I'm going to do final kinetic energy minus initial kinetic energy, again, of my whole system. Okay, so all I really do is do 1/2 mv squared twice, because EK has 1/2 mv squared. All right, so these are really all about thinking about the before and the after. So my kinetic energy at the end is going to be 1/2 times the mass that's moving, which is 10,000 kilograms, times the speed it's moving at, 1.5 squared. And I'm going to take away, subtract. The important part is I'm taking the difference here, right, to find the change, which should be negative because I'm losing. 1/2 times 3,700 times 4 squared. That's my kinetic energy at the beginning, right? I officially could think of it like this. I also have a second object, but it doesn't have any kinetic energy. So I do this minus this, punch it in my calculator. You end up getting right about, when you round it to sig figs, 18,000 joules negative, which means I lost negative energy. So I don't need to write the negative because I'm just saying that's what I lost. Here, I got it here, 18,350 or something. So again, I round to 2 sig figs, and there we go. All right, so that's a pretty straightforward one, but just an example of how to think about conservation problems. Really, like a sketch, thinking about the before and after for your whole system is the key, whether you're doing momentum or energy or what. Okay. So there you go. There are some basic ideas about net forces and conservation laws to get you started. Now you go practice a whole bunch of them and see how they go. All right. Good luck.